Now, let's see what happens when we input a complex exponential to a linear time invariant system. What do we get as a response, as an output? So we're going to do just the same as we did for discrete time signals. We're going to put this inside the convolution integral. So assume that we know the impulse response of the system. Okay, it's the impulse response. Then y of t can be written as the convolution of the input with the impulse response, right? So we cast the integral x of tau, h of t minus tau, d tau. Now I'm going to use the permutation property of the convolution. Permutation. Just to be able to write it like this: h of tau, x of t minus tau, d tau. Why? Because now I will put our exponential here. So minus infinity to infinity, h of tau. Well, x of t is e to the j omega 0. This is some frequency. I put the 0 here just to denote that this is a scalar and not an independent variable. So e to the j omega 0 t. So we just put t minus tau wherever t appears here. So e to the j omega 0 t minus tau d tau. Now we can separate these exponents. H of tau, e to the j omega 0 t, e to the j minus j omega 0 tau d tau. Now notice that inside this integral, tau is our independent variable. So as tau doesn't appear here, this is a constant inside the integral. So we can put it outside, multiplying the whole integral. So e to the j omega 0 t minus infinity to infinity, h of tau, e to the minus j omega 0 tau d tau. Now recall that we use tau as an independent variable inside the convolution integral just because t is already used as a constant, which represents the shift in time, right? This t comes to here, so we have to use another symbol, in this case tau, to denote time as an independent variable. But here we no longer have t in this formulation, so we can come back to use the symbol t. Okay, so we have e to the j omega 0 t integral h of t e to the minus j omega 0 t dt. So what we have is exponential in, exponential out. So our y of t will be the very same exponential that went as an input multiplied by this thing that we will call h of omega. In this case, as I'm using this symbol here, omega 0, age of omega 0. So again, just like in the discrete time case, we see that, let me put this a bit more down, when x of t is an exponential, a complex exponential of this type, if it is an exponential, then the output will be the same exponential, just multiplied by some scalar, some complex scalar age of omega. So the value of this scalar depends on the frequency, on this frequency, of course, and it will just distort the exponential. So it will impose some amplitude, gain, and some phase. Actually, we can write this age of omega 0 in this form, some amplitude times e, some amplitude which also is a function of omega 0 times e to the j omega, some phase e to the j, some phase omega, some phase which is also a function of omega 0. So amplitude and phase. So omega 0 can be visualized in the complex plane, real and imaginary. Let's say it is somewhere here, age of omega 0. So it has phase phi of omega 0, and it has amplitude a of omega 0. Okay, so it will just distort the exponential. The frequency of the exponential will be the same. So we can write this, we can put this in our formulation of the output. Y of t equals some amplitude times our very same exponential that went in, and here I will add the phase plus phi of omega 0. Okay, so exponential in, exponential out. In this slide, I'm summarizing what I have written here. We have here the formulation for age of omega. So for any impulse response age of t, I can obtain a frequency response. That's what we call this age of omega, frequency response, which is how the system responds to an exponential with that frequency. So this is a function of omega. And for many cases of impulse responses, we can obtain a closed form solution for a closed form formulation for age of omega. Let us do an example here. We have this system, a system which has this impulse response, which is zero-centered moving average filter. Okay, notice that this filter has to predict the future, right? Because it's doing the average from half a second back in time to half a second in the future. So it is what we call a non-causal system. It's impossible to implement such a filter in practice in real time because it would have to foresee in time, it would have to predict what the input will be. But in the end, the formulation of this guy is simpler and easier to derive than the causal case. This is why I prefer to show this example. Okay, let's put this inside the formulation of h of omega. So the frequency response is the result of this integral, h of t e to the minus j omega t dt. Notice that we're integrating across t, so t shouldn't appear in our resulting formulation. We should find a function of omega. So we hope not to see t in the result. So this guy, it's just 1 from minus half to 1/2. So I can just change the limits of the integral, right? From minus half a second up to half a second. Then I can just neglect this part. And we have just e to the minus j omega t dt. So what we have is we have to pass this guy dividing, right? 1 over minus j omega. And here e to the minus j omega t with t ranging from minus half up to half. 1 over minus j omega. Here e to the minus j omega half minus e to the plus, minus with minus gives us plus, e to the plus j omega half. Now, as I have minus sign here, we can swap the signs inside this subtraction. So we get 1 to the j, 1 over j omega, e to the j omega 0.5 minus e to the minus j omega 0.5. Now we will use Euler's formula, this version, which allows us to break a sign into two exponentials, two complex exponentials. So the sign of x is 1 over 2j e to the jx minus e to the minus jx. This is just a consequence of the more well-known Euler's formula, which is e to the jx equals cosine of x plus j sine of x. This is a consequence of this formula. You can check it. You can substitute it here, and here you will find the sign. Okay, so Back to our subtraction there. We will have to make we'll have to make a number 2 appear here, right? So we will multiply by 2 over there. So we have 2 equal, yes. 2 over omega times 1 over 2j and the 2 exponentials. And here we can see that this is a sine, right? So we have 2 over omega times the sine of 0.5 omega. This is also 1 over 0.5 omega, right? So in the end, we have the sine of 0.5 omega divided by 0.5 omega. So yes, we have found a expression for the frequency response of the system which has this impulse response. So if you have this impulse response, the frequency response you have is sine of 0.5 omega over 0.5 omega. Notice that here our independent variable is omega. It is just a function of omega. So if I input any exponential to the system, what I will have in the output will be an exponential with the same frequency, and in this case the same phase, because this expression has zero angle, zero phase for any value of omega. I will just change the amplitude of the signal. So for instance, an exponential with frequency 0, which is a constant, if I input it, I get the same constant in the output. If I have an exponential with this frequency here, I will have something with inverted amplitude, with negative amplitude. Notice something interesting here. There are some frequencies for which the output has zero amplitude, right? And we can actually visualize why this happens. It's in the it's for 2 pi, 4 pi, 6 pi. So in this system, I will have a zero output for frequencies which are integer multiples of 2 pi. And here we can see why in this graph. When I have, for instance, here a cosine of 2 pi, my average filter is always integrating half a period. No, sorry. It's always integrating a full period of the input signal. And if I integrate a full period, I always get 0. This will happen for frequency 2 pi, 4 pi, 6 pi, and so on. In this slide, I've separated this into 2 graphs, one for magnitude, amplitude. So here's the absolute value, that is the magnitude of the frequency response, and here's the phase. So for this case, where I have only real values, all the phases will be either 0, or pi or minus pi. So when I have negative gain, when I have negative amplitude, I will get either pi or minus pi angle. Now, why do I say this pattern? We know that in terms of angle, pi and minus pi are just the same angle. So why did I choose to represent this side with minus pi and this side with plus pi, if they're the same? It's just to respect one important property of frequency responses, which is the following. This property here, which states that if h of t is real for all t, so if the impulse response, our impulse response is here, is real, and in this case, in this course, it will always be real. So this property is really general for us in our context. Then I have two consequences. One is that the absolute value of h of omega will be symmetrical. So if I take some omega here, for instance, 5 pi, the h of minus 5 pi will have just the same magnitude, the same amplitude. And the opposite happens with the phase. For the phase, we have this, the phase of h of omega is the inverse of the phase, inverse sign, okay, of the phase of h of omega for omega with inverted sign. So this one is anti-symmetrical. So this is symmetrical, and this is anti-symmetrical. And this will always happen when I have a real impulse response. And you can actually derive this property from the fact that this is multiplying, that this is cosine of omega t plus j sine of omega t. So this is a odd function, this is a even function, so this is anti-symmetric, this is symmetric. You can, if you like, you can derive this property from the formulation, the very formulation of frequency response. Okay, so we have here one example. We obtained a formulation for a frequency response. Let's see another example, this time for an electric circuit. In this case, I will not start with the impulse response. I will derive the frequency response formulation from the circuit diagram, right? So if you already studied electric circuits, you might be familiar with phasors. So that's the tool we're going to use to find the frequency response here. So we have to draw the equivalent circuit with the impedances. So X of omega, the impedance of a resistor has just the same value of the resistance. The impedance of the capacitor is XC, which is 1 over J omega C. And the output is for this first example here, right? So HR of omega will be just this impedance divided by the sum of both of them. This is an impedance divider, right? It's a simple example of an electric circuit. So I have just, this is R, okay? Let's just keep literals. R over R plus 1 over J omega C. And that's it. That's the frequency response for this circuit. Then we just substitute the values of R and C here, and we get a numerical expression. We can alternatively multiply everyone here by J omega C. So we have just J omega RC over J omega RC plus 1. This is just optional. I've created here a script where I plot the frequency responses of these two cases. Here's the case where we have the output in the resistor. So I created an array of frequencies here for which I want to assess the frequency response. It goes from minus 5000.1 radians per second up to 5000. Why this 0.1 here? It's just because I want to avoid the division by 0. I don't want this array to have the 0 frequency, so I don't have the division by here. 0 here and here. Here it won't happen, but here in the definition of XC, the impedance of the capacitor. So array, scalar. This is an array because it's the result from an operation between scalars and this array. And then here an array of the values, the raw values of the frequency response. And then I'm plotting them as magnitude and phase right here below. So we can notice that this system is a high-pass system or a high-pass filter. It's a first-order high-pass filter. It has zero gain for zero frequency. So if I input a constant here, which is a constant signal, is just x of t equal e to the j omega, where, well, in this case, omega is 0 t, so e to the j 0 t is 1. If I input the constant 1, what I get in the output is 0, because I will multiply by 0 here. And for very high frequencies, it just gives unit gain. Okay, so this is a high-pass first-order filter. Then the second case here, the system where the output is the voltage over the capacitor instead of the resistor. We do just the same process. We draw the equivalent circuit, R, X, C. The only difference being that now the output is the voltage over the capacitor. So our frequency response will be this over the sum of these guys. So XC over R plus XC, which is 1 over J omega C over r plus 1 over j omega c. We can leave it like that, or we can multiply everyone by j omega c. If we do multiply, we get 1 over j omega r c plus 1. So it's just the complement of the above case, right? Then let's see what we get here. It's actually the order is inverted here in the script. I'm plotting first this second case. So we have the complement, we have the low pass system. So this is a low pass filter, a first order low pass filter. Now if I input 0 frequency, I get unit amplitude in the output, so the system will not change an exponential with 0 frequency. For very high frequencies, the gain is really low. So this is a low pass filter. Here's what happens with the phase. Notice that we observe that property, which is, where is it? This one. This property can be observed also in this example, in these two examples. We do have, in electric circuits, we do have always real impulse responses. So the magnitude of the frequency responses will be always symmetric. The phases will be always antisymmetric. Okay. So next topic, and the last for this video, is we're going to do the same. We're going to plot these two frequency responses again, but this time in log scale, in logarithm scale. So I have a copy of the script here. It gives us the same result. So we will perform some changes here in order to get things expressed in logarithm scale. First thing we'll do is we're going to show the frequencies in a log scale. So wherever I have a plot here, I will do semi-log x. That means I want a log scale, but just in the horizontal axis. This is why I have semi here, because I don't want a log scale in both axes, just in horizontal, just in the x axis. Here again. So let's see what happens. Okay, a different visualization, but notice that the negative frequencies are not being displayed, and this is why there's no log of there's no real log of negative numbers. So we can actually remove them from here. We can go from 0.1 to 5,000. We get basically the same result. We can go further. For instance, we can go to 10,000 to see what we will see. So this is the general shape of the curve. So what happens if I go to 20,000? The shape doesn't change. So if I show where are my points here in the plot, where is the plot? Here. if I choose this marker, we will see that this should be here. We will see that they're not evenly distributed, right? Because I arranged them in a linear scale, and here they're following, they're being plotted in a log scale. If we give a step of 100, maybe this will be clearer. Yes, okay. So not an even distribution. We can solve this. We can use this function to define the set of frequencies for which we want to assess the frequency response. We can use log space. So I want to go, for instance, from 10 to the minus 2 up to 10 to the 3, 4, up to 10,000 with 100 points. Then 100 points is not that much, but they're evenly distributed in a logarithmic scale. So it's nicer to visualize. I can remove this. Okay, what's happening with the phase? There's a shift of phase here. Can we go further? Yes, we can. Let's go up to 10 to the 6 here. Yes, we can see these two shifts in the shape of the amplitude frequency response, and this shift in the phase. Then what else can we do? We can also plot the amplitudes in a log scale. Okay, the amplitudes. There's no reason to see the phase in log scale, but the amplitudes, that would be interesting, because here we have some variation of the amplitudes in a very, very small range. So it would be interesting to see more clearly what's happening here. So we can do here log. Then we will see log scale in both axes. So in the horizontal axis and in the vertical axis. And finally, we can use a dB, a decibel scale. We come back to semi-log x, and instead of asking the plot function to do the log, we will do the log here. So np.log10. If I do the log in basis 10 and multiply by 20, I get what we call a decibel scale. Decibel scale. It's also called dB scale. So now I have to make it clear here, dB. Okay, so magnitude in decibel, and here's the phase. And that's it. We're doing the plot in a log scale. In this case, a dB scale, decibel scale. Let's do the same for this second case. It's the semi-log x here instead of plot. Here I put 20 np dot log 10, and here again semilog x. And there it is. One thing that I forgot to show you is that if I sum, let's come back to the linear scale to do this. If I sum both of these frequency responses, I get a unit frequency response, okay? And here's the same. I'm summing them here below. So let's use the semilog x, 20 and p dot log 10 of the absolute value. I'm calling it age of t for total. I'm having basically one here. One, which in dB scale means 0 dB. So this is basically 0 because it's multiplying by 10 to the minus 15 and 0 phase. Okay, so this visualization of frequency responses in logarithm scale is related to the activity that I'm leaving for you, where you have to show the frequency response. This is a very ugly drawing, but I think you get the idea. You have to show the 3 frequency responses here. In the 3 cases, the input is this voltage source. The first case, the output will be this voltage. The second case, the output will be here. Third case, output here. And then there's a fourth case where you have to sum all of them, where, as you might expect, you will get some unit response. Okay, so that's it for frequency response.